We got two hand rules that we learned about yesterday. The first one's called the wire grasp rule. And you're going to remember from yesterday that the wire grasp rule is used whenever we've got a charged particle that's moving and we're trying to find the magnetic field that's caused by that moving charge. Simple as that. Now, that charge may be moving through the air or through a liquid, like a sodium ion moving through water, or it may be electrons moving through a copper wire. It doesn't matter. In the end, those moving particles generate a magnetic field every time. Let's say that those moving particles are moving away from us, as indicated by the X here right now. What's the shape of the magnetic field that's caused by that moving negatively charged particle? What's the shape of it? Yeah? Don't give me the direction right now. Just give me the shape of it. Yeah, it's circular, right? In fact, we have a series of concentric circles, and those circles, as you know, get further and further away from each other, indicating that the field strength gets weaker as we get further away from the moving charge. Now, how do we figure out the direction of that moving charge? Sorry, of the magnetic field caused by that moving charge? Yeah, we're going to use this wire grasp rule. And because this is a negative particle, we're going to use our left hand. If it was an alpha particle or a sodium ion, we'd use our right hand. Left hand for negative particles, right hand for positive particles. How do you use that wire grasp rule with your left hand there? Nick? Yeah, thumb goes into the page because that's the direction of the particle. Our thumb goes in the direction of the particle, and then? Yeah, we bend our fingers. Now, how far do we bend them? Like this or like this? It doesn't matter. Because in the end, when we bend them, no matter how much we bend them, we're going to see that the magnetic field ends up going counterclockwise here. Now, if we've got a positive particle going out of the page here, this time we got a positive particle, going into the page, I should say, same shape of magnetic field. The field lines are getting further away from each other, just like the negative particle, but the direction might be different this time. So let's try this one. With our right hand, because it's a positive particle, thumb goes into the page, fingers get bent, and you're going to find that your fingers, no matter where you put them, no matter how much you bend them, are going clockwise. So we have a clockwise magnetic field there. What about this one? This one is the one that people struggled with a little bit. What if we've got a charged particle that's moving this way? Actually, let's say we have conventional current traveling to the right. What do we mean by conventional current versus the electron current? Yep. Yeah, the flow of positive. So let's say we've got our right hand. We want to find the magnetic field strength surrounding this. If we use our pen as our moving charges to the right, then we would say the magnetic field goes this way around it. That's kind of hard to visualize in a two-dimensional paper. So usually what we do is draw symbols above, below, in front, and behind. Above the wire, or above the alpha particle, the moving alpha particles, we're going to say, whatever they are, we're going to say that the magnetic field points, this is the page, magnetic field points which way? Don't put your fingers like kind of above it. Put your fingertips, your fingernails right above it, directly above it. And which way do they point, Fernanda? This is the page, yeah? Yeah, away from the page or out of the page. Good. So above it, we're going to represent it by a dot. Below it, my fingers are pointing into the page. In front, my fingers are pointing, Tristan? Down. Don't say down. Towards the bottom of the page, good. If my frame of reference is north, south, east, west, then you can say up and down. But if my frame of reference is the page, then you want to say top of the page, bottom of the page, right? We're going to say there towards the bottom of the page, and in behind it, you can see that my fingers are pointing, Cody? Up the page, yeah, or towards the top of the page. We're going to draw that with a little break in there, indicating that it's in behind there. That make sense? So the quick little summary of this is, well, we got two variables. We've got our thumb, and we've got our fingers, our bent fingers. Our thumb is going to point in the direction of the moving charge. And our bent fingers are automatically going to point in the direction of the magnetic field. The magnetic field, that is, it's caused by the moving charge. Now, we also learned yesterday about another rule, which we called the Coil rule. The Coil rule is used when we have a coil of wire. Do you guys remember the other name for a coil of wire? The fancy name that sometimes people use to make themselves sound smarter? It's a solenoid. Okay, a coil of wire or a solenoid. Usually in a solenoid, or a lot of times in a solenoid, we have a core, a ferromagnetic core. And the reason we would have that is to kind of store the magnetic effect that's caused by the electric current going through the wire. We don't really need that core, but it helps, and it also makes it easier to visualize the diagram. So I'm going to draw a core that's made out of steel or cobalt or something that's ferromagnetic, and I'm going to draw the wire wrapped around it. This is my actual solenoid, or my coil of wire, with a battery hooked up to it. What's the positive terminal of the battery, the short end or the long end? The long end. Yeah, this is positive, this is negative. If we were talking about electron current, okay, electron current, then it would be going this way, leaving the negative end, going up in the front, down in the back, and then around to where we started. If we were talking about conventional current, then it would leave the positive end, go up in the back, and down in the front. Right? Electron current leaves the negative side of the battery. Conventional current leaves the positive side of the battery. It doesn't really leave the positive side of the battery, but that's the way we visualize it. Now let's get rid of that conventional current, because we rarely use conventional current to deal with the problem. Only if the question states that. And like I said the other day, it's probably maybe 5 or 6 times in the last 20 years that they've used conventional current on an exam. So let's figure out what the polarity of this coil is, or polarity of the solenoid is, using electron current. Let's take out your trusty manipulatives that you made yesterday. The piece of paper that were wrapped up here with the word front on it and the word back on it. The coil rule is similar to, but different from, at the same time, the wire grasp rule. Instead of saying thumb current, fingers field, we're going to say fingers current, thumb field. We know which way the current points here. That's not a magnetic thing at all. That's just which way the battery is oriented. We're going to say our current in the front points upwards, as on the diagram. So what we're going to do is take our manipulative with the word front on it, look at the word front like I am right now, put your fingers, your left hand fingers, because we're talking about electron current. If it was conventional current, we'd use our right fingers. Left fingers on the word front, not near the word front, on the word front. Look at your fingertips. They should be right covering up the word front. Now, bend your hand around so that your thumb automatically points to the right. If your thumb automatically points to the right, then that means this end of this solenoid, which has become an electromagnet, is the north pole. This is the south pole. Didn't we say the other day that magnetic field points from north to south? Here we got it pointing from south to north. Yeah, Caitlin? Good. Outside the magnet, it points from north to south, but inside the magnet, it points from from south to north. So this is correct. Got it? Now, let's say we've got one like this. We got our coil wire wrapped around it like this. We got a battery hooked up to it, but I'm not telling you what the polarity of that battery is. Rather, I'm going to give you the magnetic field outside of this coil, or what's become an electromagnet here. It's pointing this way, from the top down towards the bottom. What do we know about the polarity of this new electromagnet as a result of this electric current? Yep. Right? So like this? Okay. Yeah, good. Good. It's important to recognize the polarity of this. We don't need to go through a hand rule to recognize the polarity, because we already have the magnetic field. Most of these questions that you'll see will be like this, where you're given the current and trying to find the magnetic field. But every once in a while, you're given the magnetic field, you're working backwards to try to find the current. That's what we got here. So we know the magnetic field now, thanks to Cody, is pointing upwards, inside the coil. Okay, look at your coil, your piece of paper wrapped up, it's become your coil. Look at the word front that you wrote on that yesterday. And then make sure with your left hand that you stick your thumb pointing upwards. Then move your hand around wherever you need to move it so that your fingers are on the word front. So my thumb points up. I know it should point up because Cody told me the magnetic field inside is upwards. My fingers in the front will be pointing to the left. That means the electron current in the front will be pointing to the left. It's going to curl around like this. What's the polarity here? Short end or long end right here of the battery? What is it? It's going to be the long end, right? Because it's got to be the positive terminal. This has got to be the negative terminal because the electrons are leaving here and then going around counterclockwise. Is that okay? Can you tell me a way that I could make this electromagnet stronger? Yeah, what's one way? Yeah, increase the current, more electrons going through there in a certain amount of time, so stronger current. Cody, what's another way? Sure, more coils around it, right? More turns of wire. Right now I have what? 4 turns of wire around it. If I put 8, then that would double the magnetic field strength, right? Anything else? Move the coils closer together, you mean? No, that's not going to have a significant factor there. If I have the number of coils there is 4, it doesn't really matter if they're, you know, like that or not. The biggest thing is the biggest thing that I would think of is the amount of current. Okay, of course the amount of current, and of course we have the number of coils there as well. Yep. Yeah, well, that's if you had another. Yeah, no, I see what you're saying there. That's if you had another one, right? Like if you had another magnet down here, and we wanted to affect the force between them, then the closer they are together, sure, is going to create a stronger magnetic force. The question this one time though was, what's going to increase the magnetic field right here? Right, what's going to increase the magnetic field? The number of turns and the amount of current that goes through it. All right, does that make sense? George, the difference between yesterday and today? Okay.